Hello. Hello. Thank you so much for waiting. Good morning. Good morning. All right. Sorry about the delay. Thank you. I seems like I hope you guys got the message. Thank you for your flexibility and patience. So sorry. Okay, I'm going to say good morning in the official way, but I know it's late. I hope you got the message that it was late. I think maybe some of you did. If you didn't, thank you for hanging in. If you didn't, but yes. Okay. Good morning, Jayla. Good morning, Alyssa. Good morning, Noel. Good morning, Lakshmi. Good morning, Charlie. Good morning, Soad. I really appreciate it again, sir. And good morning, Jayla, and good morning, Rydia, for not black boxes. Oh, and good morning, Vivian. I'm sorry. But I am truly sorry for starting late. Again, I do hope I sent a message, but I sent the message very late. So I hope that some of you guys, well, actually, can I just ask, are you here? Did you get the message that we were starting 11, or have you just been suffering in yes. Okay, cool. All right. Thank you. Okay. That's a relief. It still doesn't excuse it. It doesn't excuse it. It doesn't explain it. It doesn't forgive it, but thank you. Okay. But I'm glad you're here. I'm glad we're here. I probably lost some other people. I bet some other people came at 10:50 and then gave up and went off and torched my house, which would be fair. I hope they used a proper torch. Okay, but we're going to start. Okay, but thank you again. And I will say, we're continuing with the concept of average acceleration and instantaneous velocity, i.e. really what that really means is I'm going to continue talking about the thing that happened right at the end of class last time, but specifically the stuff that happened right at the end of homework 4, which I'm not going to, but it was right at the end. So I don't even think it's necessary for me to, I'll remind you what the problem was that we were talking about. I mean, I'll remind you in a moment. I don't think it'll be necessary to switch screens or anything like that. But we did right at the end of last class, we got to a new equation. Thank goodness. We're starting now, progressing through some new equations. The new equation we got to is right here in the center of the page. We haven't really, and that's just literally where we got. So, and I hope you do write it down again, and I hope you write the thing underneath it. I'll try to explain that. Some more people coming. Hold on. Yeah, we had just, so right at the end of last time, we had just gotten to this. What I feel like if you were with me and everything, what was going on at the end of homework 4 is that I was trying to demonstrate the meaning and the truth of this. And I was trying to demonstrate it with just sort of raw numbers, showing you how raw numbers work. And then asking, and I'll say it again in a minute, but the point of the end of homework 4 and the point of last time was to not technically prove, but informally derive, i.e. justify this equation. Like, I'll run through the argument again sort of briefly, but the hope of the last part of homework 4 is that you would now have good reason to believe this equation and believe that it makes sense. Like, I'm really struggling. In other words, every time we get an equation, we're really not trying to just have some new formula that we just accept and then memorize and use when applicable. In fact, honestly, this is one of the reasons you'll sometimes see me react on exams or homework or even in conversations. I don't like the word formula, at least not in this context, not in physics. I like the word equation because an equation is just that. It says that whatever's on the left side is equal to whatever's on the right side. And like all equations, like an equation means also whatever's on the right side is equal to the left side. Generally speaking, an equation is either a triple equal sign or a double equal sign. Like, it's either a definition. So it just means, like, we're saying from here on in that these terms that we're using on the left that we think are kind of short and symbolic and efficient are like stand for all these other terms on the right-hand side. Like, often a lot of our equations are really just, and that's why I love the triple equal sign. They're often just saying, look, from here on in, these are two different ways of saying the same concept, right? And whenever they're that, then that's a reason to believe them. As long as you understand what the concept is and the words behind it, then if a definition is ever true, then it's always true, right? So that's triple equal sign. Then sometimes we get into double equal signs equations like this one. In fact, honestly, to everybody, this is our first equation at all that is a double equal sign, not a triple equal sign, meaning that this is not a definition. Now, in fact, okay, I'm going to turn the page. Like, I will back up and try to explain what it is a little bit more, or why we believe it as per homework 4. Then, of course, I want to start using it. I mean, that's like the main thing, is to really use it, but it's pointless to try to dive in and use it if you don't know what it means, or you don't like see why it makes sense. So note this before I go any further, or note the following before I go any further. Okay, just to be as clear as possible, we have 3 equations so far in this class. We have 3 equations, okay? The first 2 are triple equal signs. They are just literally definitions. If they make any sense at all to you, then hopefully they always make sense. And if they make any sense at all to you and they seem ever reasonable, then they are always that reasonable. They're just saying like average velocity means this, average acceleration means that, right? Okay. Then we get to our newest equation, the equation we just got to at the end of last class. Now notice 2 things about this. One, this equation is, even though we only have 3 equations, 2 of them are like in reference to the same concept. 2 of our equations are both about average velocity. They both have v bar on the left-hand side, right? But they are not a contradiction to each other, nor are they redundant. What they can be to some people sometimes, if they don't see all this, it can be confusing, because for some people it's like, oh yeah, I have 2 equations for average velocity. So if I ever get to a problem in life or on an exam or on the homework or something, and I know that it has something to do with average velocity, and I need to do something with average velocity, how do I know which one of these to use? Or like, are they both, you know, how do I know which one to choose? Is actually often a question. By the way, by the time you consciously ask that question, you're probably on the road to answering it, and you'll probably be okay. The really disturbing thing is that it's often a question unconsciously in people's minds. Like they'll be doing something and then they hit a glitch because they don't realize it, but what's going on in their minds is like, oh, I need to deal with average velocity now, and I've got 2 equations for average velocity, so I don't know which one to use, and I have no idea what to do, right? So here, that's often going on without people realizing it's going on, especially early on when we only have this few equations. Let me tell you what to do. First of all, notice that the first equation for average velocity is a definition, i.e., it is always true. The second one is not always true. So first of all, when in doubt, you should always start, really almost any physics problem, or certainly of this type that we're dealing with here, if there's any issue about average velocity or any possibility that average velocity has anything to do with what you're doing at all, always start with using the first equation. That's why we started the year with it. Use it to the, and if you have all the information and if you can get anywhere with it, then that's it. That's all you should use. You should always rely first on the first one. It's always true. If the worst thing that the first equation will ever be is irrelevant, like, right? It might turn out that you don't have enough information to use it or something like that, but it's never going to be wrong. put more bluntly, especially if we have an exam coming up, which we sort of do, which we're going to start talking about. If you're on an exam and you write down that equation in the context, if it's even remotely relevant, if like we're even dealing with motion at all, which we always are, if you write down that equation, you're going to get points, some points, because it's true. It's like, right, it can't be wrong. The worst thing is you just might not know what to do with it after that. So you might not get all the points, but okay, you get that. So what's the deal with the second equation? The second equation is sometimes true. It is a different way of getting average velocity. It's a way of getting average velocity when you don't have information about the time, for example, when you have other kinds of information. What the second equation says, what we actually found last class, what this says in English is, if you can read this. Now, I said this quickly at the end of last class. I don't know if you can read that red. Maybe you could tell me in the chat. Maybe someone could tell me either now or later, like if that light red just doesn't even work at all, if it's even a waste. I don't know if you can read it at all. But what I'm saying here is that new equation that we just got at the end of last Wednesday, what it says is sometimes under special conditions, and the special conditions are A equaling A naught. I'll be clear about that in a second. But what we're saying here is sometimes under special conditions, then average velocity is, in fact, the average of velocities, the average specifically of two velocities. When I say the average of, I specifically mean look at what's happening on the right-hand side there. The right, which again, a lot of people try to memorize or they get confused. They're like, oh wait, one equation is like, it's like a minus and it's over t. And then the, not over t, like come over to my house for like crumpets. I don't mean over t. I mean, the first equation is like x minus x naught divided by time. But the other equation is like v naught plus v, and it's divided by 2, and people like try to memorize, and then they get it all grinding. They start grinding and they're like, oh, I have v naught plus v over t. Is that? Don't try to memorize them. Don't try to memorize them. Just try to understand them. The first one is saying displacement per time, like as in miles per hour. That's the definition of average velocity. But the second one, look at it. I mean, again, I'm not yelling. I mean, I'm yelling because I'm excited, not because I'm angry. But I'm yelling partly because I know I personally, like I was a physics major, for God's sake. I probably took 2 semesters in physics before I ever really saw that on the right-hand side of that last equation, it's literally saying take 2 numbers, add them together, and divide by 2. It's literally saying average the velocities in order to get average velocity, right? And the 2 velocities that it's asking you to average in that final equation are the first v naught, like initial velocity at time equals 0, i.e. the velocity that occurs at the very first moment you're paying attention, taking data, starting your stopwatch, observing the experiment, right? So v naught, the very first velocity, plus any other instantaneous velocity, the one we usually call the final velocity. In other words, the last velocity, the velocity when you stop paying attention, or the other velocity you're paying attention to. Like you could, I guess also what I'm trying to say is you've seen this in books a lot. You might see this in book. Well, hello. Like if it helps, another way you could write this equation, sometimes in books, people will write this equation as VI plus VF over 2, as in initial velocity plus final velocity over 2. Otherwise, some other books will write like V1 plus V2 over 2, if you like that. We're just saying it's 2. Oh, I don't know. Oh, you'll see in a second. I don't know why the thing is going bananas. Okay. You see there in black, like some books will say V average equals, and I'm talking about the double equal sign one now, like not the definition, but I'm saying some you could write it any way. Average velocity is the average of two velocities. What two velocities? The beginning and the end, like the first and the last, the initial and the final, the number one and number two. Beginning end of what? Of whatever you're paying attention to. Could you pay attention to something else and get two other velocities? Sure. But then the average you'd be talking about is the average between those, right? So what this is saying is sometimes the average velocity over a region, like throughout some region of time, throughout some region of space, sometimes the average velocity is literally the average for that interval is the average of the first and last velocities of that interval. That is what this thing is saying. Okay, and in some ways it makes so much sense. Like it's literally saying the average of the velocities is the average of the velocities. It makes so much sense that it almost wouldn't be interesting, and it almost would be the equation that we start the whole year with, except that if you're really paying attention to this class, and this is where you'll notice that in fact, like 2 of the 3 early problems that we gave on homeworks about average velocity were designed to show you that you shouldn't always believe this. Like it's such an instinctive thing to believe that people were believing it without using an equation. They were just believing in their heads. Like there were at least 2 problems we did, one called Grandma Grimm and one called Hill Figure, right? And we did in the opposite order. And Hill Figure, like you go up a hill at 40 miles an hour, then you come down the same hill at 60 miles an hour. And we asked, what's the average speed for the whole round trip along that hill? And of course, most people instinctively are like, oh, average speed. Okay, I'll just average the speeds. 40 plus 60 divided by 2 is 50. Hello. And then my ranting point for like 3 days that might have felt obnoxious to some people, not meant to be obnoxious, but I was like, aha, you think average speed is the average of the speeds? Oh no, silly knave, no. Average speed is distance over time, or average velocity is displacement over time. And I was making this big point, like, don't just assume naively that the average velocity is the average of the velocities. Don't think you could just take 40 and 60, average them and get 50, because actually the answer for that hill is actually 48. And I'm not taking any of that back. I mean, this is where physics is very simple. Physics is very simple, but not very easy. Like each concept makes sense. Each concept is supposed to be small and have something to do with something that actually fits in your brain and is actually not being just made up with black magic formulas or cauldrons of wizardry. It is supposed to make sense, but it's a lot of little things that all make sense that are stacked together that start changing our sense of sense. Okay, so I'm not taking any of that back. None of it's meant to be obnoxious. None of it's meant to trick you, but it's supposed to reveal the trickiness of the game here. What we were saying when we went up the hill and down the hill, and we said up at 40, down at 60, but the average is 48. What we were saying was, hold on, it's not always the case that you can average speeds or velocities in order to get an average velocity. What's always the case is that average velocity is displacement per time. That's what's always the case. That is the meaning of average velocity. Now, sometimes, under special conditions is what we're now saying. And now I'm going to like expand on those condition stuff. What we're now saying that we feel that we've discovered, looking at a bunch of raw numbers last class, and again, I'll go back over them sort of in a second. But what we feel like we're discovering now is, oh, that's not crazy to think that you could average velocities in order to get an average velocity. Is just a very specific point that you have to be very careful about. You can't always do it. You can't do it in the case of that hill, for reasons I'll say again in a second. But there are special conditions under which you can do it. IFF, what it says here, IFF, that means if and only if. And so that means special condition coming, right? If and only if. If A equals A naught, it says there, right? And then that's supposed to be a colon, like that. So that's like the if condition. If A equals A naught for a given situation, for a given region of time, for a given region of space, if A equals A naught, then not only does average velocity still equal displacement over time, like it's still defined that way, but also in addition to that, we're saying, not contradicting, we're saying it also turns out that yes, say you don't have all the information about the time or something like that, you can also get average velocity by averaging the first and last velocity, i.e. adding them together, dividing by 2. You can get average velocity by averaging the velocities. In fact, as long as A equals A naught. And what do I mean by A equals A naught? I mean, as long as the acceleration at the beginning, like A naught, what is it? Anything naught, anything with a subscript 0 always means the value of that variable when time equals 0, which means when we started paying attention, when we started collecting data, right? Okay. So if A equals A naught, it looks almost like redundant. Like, what is that? No, that's very specific symbolism. That means if A, the value of A of acceleration at any given moment is the same as whatever it was right at the beginning. That's what that notation means. By the way, we can use that same notation to say something like if V equals V naught, or X equals X. What that notation means in this case is if A is a constant, if acceleration, so we're like talking about two new things here at the same time. I mean, we're talking about this new idea of acceleration, which is explained in or defined in equation number 2 here. Acceleration is change in velocity. That's what definition equation number 2 says. Average acceleration is change in velocity. We're now saying if that change could be occurring, like velocities could be changing, like a car could be getting faster and faster and faster, or it could be getting slower and slower and slower. And if it does, then that means we have acceleration and we're to a new, slightly more complex or rich or interesting realm of physics now. Once things are speeding up or slowing down, we call that accelerate. If they're changing their velocity at all, frankly, even if they're changing their direction, then they are accelerating. If, and only if, the rate at which they're doing that remains constant, then the average of velocities is, then the average velocity is the average of velocities. Meaning, I think I'm about to turn the page. I think it's about time for me to turn the page. But meaning like a car could be getting faster and faster, but as long as it's doing it in a steady rate, like as long as it's going 10 miles an hour, and then an hour later it's going 20 miles an hour, and then an hour later it's going 30 miles an hour, and then an hour later it's going 40 miles an hour. If a car is doing that, that means it's accelerating, i.e. changing its velocity, but it's not changing its change, right? In calculus language, that would mean as long as the car has a first derivative of position with respect to time, velocity, and has a second derivative of position with respect to time, acceleration, like as long as there is a derivative called velocity and there is a derivative called acceleration, but there's no third derivative, as long as there's no change in the change, right? As long as it's, so as opposed to a car going like 10 miles an hour, and then going 20, then going 40, then going 70, like that would be an accelerating acceleration, if you know what I'm saying. Technically, it's called a jerk. Technically, this is called a jerk. But as long as the car is actually speeding up or slowing down or changing direction in a steady way, then the average is the averages, meaning like, yeah, if the car is going 10, then 20, then 30, then 40, then for that interval, its average velocity is 25. So I'm going to put, that's what we actually discovered at the end of homework 4, last class, just looking at raw numbers and how raw numbers work. Okay, I'm going to turn the page. I'm going to read this out loud. What I'm saying is just, this is a summary of what I think happened in the last problem from last week from homework 4. So again, this hopefully that makes sense to you if you have homework 4 either in front of you, if you've done it, if you have it at all. But I think this should make sense even if you don't even know what I'm talking about whatever homework 4 is. I'm saying what homework 4 was just, or the last problem had different sets of raw numbers. Okay, so picture just a set of raw numbers. It could be like the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It could be the numbers 1, 3, 5, 7, 9, 11. It could be totally random, like 2, 7, 9, 9, 3, 9, 9, 3, like whatever. Just picture a set of random of raw numbers. Now, picture the idea that each raw number could represent an instantaneous velocity. Like if I'm just picturing like 1, 3, 5, 7, 9, now I'm going to picture like, okay, that's going to represent like 1 mile per hour, 3 miles per hour, 5 miles per hour, 7 miles per hour. Like it could represent different speeds that a car might be achieving at different moments, right? Because that's what instantaneous velocity means, how fast you're going at a given moment. So picture these, in other words, as like readouts on some radar gun or some speedometer display, right? So it says, picture a set of raw numbers, picture each raw number representing an instantaneous velocity. And that means a velocity applicable to one moment in time. Now picture that, now just imagine, assume, hypothesize that there are equal time intervals between each pair of raw numbers, right? So if I say, like, I'm picturing the numbers 1, 3, 5, 7, 9, what that really means in this analogy that we're making, or in this informal derivation that we're doing, I'm actually picturing 1 mile an hour, 3 miles an hour, 7 miles an hour, 9 miles an hour. And now what it's saying here on the sheet is, now I want to add the extra feature. Let me imagine that those are readouts on some sort of speedometer or radar gun or something applicable to some object like a car. And I'm going to picture now that each one of those readouts got spat out at equal time intervals. So it's almost like a table of values. Equal, and time is the independent variable. Like I'm taking measurements every hour or every minute or every second, whatever. And these velocity numbers are being returned to me, like I'm measuring them in the dependent value column. So it's like a table of values, 1, 2, right? Okay. What I'm saying about that is, if you think about such numbers, okay? I'm going to put this back in equation form in one more minute, but I'm trying to summarize the whole thing. I'm trying to say again why I think this last equation makes sense, but it packs like 3 implications in it at once, actually. So what we're saying is if you have a bunch of random numbers like 1, 3, 3, 3, 3, 3, 13, 13, 13, 7, 9, if you want the average of those numbers, you literally have to add them all up and divide by the number of numbers. That would give you the mean of all those numbers. And that mean that you get like may or may not even be one of the numbers I just mentioned in that crazy list, right? Like if you just have random numbers, if you want to get the mean, you got to add them up, divide by the number of numbers. But if you have numbers that are in a specific kind of pattern, this pattern, if you have numbers that are in a pattern where numbers are increasing by the same amount always, or decreasing by the same amount always, right? Then if you think about it, then if you think about it and you arrange those numbers in order, then whatever number falls in the middle of those numbers really is in the middle. That is the numbers 1, 3, 5. Let's just look at the numbers 1, 3, 5, right? They're always increasing by 2. Or if I said 5, 3, 1, they're always decreasing by 2. The step between each 2 numbers is the same each time. So the number that's in the middle there, 3, it necessarily is just as far away from the top number as it is from the bottom number. In fact, even if I went further, like 1, 3, 5, 7, 9, right? 5 is 4 less than, right? If I went 1, 3, 5, 7, 9, 5 is 4 lower, like the number 5 right in the middle, 5 is 4 less than the top number 9, but it's not coincidentally 4 more than the bottom number 1, because we were always increasing by the same amount. It's not a coincidence that if I tried to represent that whole set, 1, 3, 5, 7, 9, if I tried to think like what number best represents like the whole thing, if I said 5, that really is a good thing to say, because 5 is off, like it's off. It's not the top number, it's off from the top number, but it's lower than the top. It misrepresents the top number by exactly the same amount as it misrepresents the bottom number, because everything is changing in the same way. Like that's not true, right? If I go like 1, 4, 9, 16, 25, 36. Now that's a pattern. That is definitely a pattern. And that's very interesting how those numbers are organized. It's the perfect squares. It was the last set of numbers on the homework 4 exercise, blah, 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 blah. That's a pattern, but that's too complicated a pattern. Like, because then like from 1 to 4, I'm increasing by 3, but from 4 to 9, I'm increasing by 5. From 9 to 16, I'm increasing by 7. Now, yes, you can even see that a pattern starting to develop there, but it's already too complicated. Like, in other words, the number that's in the middle there is much, much farther away from the top number than it is from the bottom number, because the increases are increasing as you go, right? So what I'm saying is, as long as the increase or as long as the step is always the same, as long as you're increasing or as long as you're changing by an unchanging amount, then the number in the middle is the average of all of the numbers. You can bank on it, so much so that even if that number doesn't appear in the list itself, it still is the average. In other words, and people pointed, even if you have an even number, I want to say a lot of people have done homework 4, like not everybody. I mean, technically it was assigned, whatever. So a number of people have done it, and I'm very impressed, very proud of those of you who did it, like went, it was assigned. And some people even redid it already based on what I said in class, like last 2 days, and people got great scores on it. Almost anybody who's done it, I think, has gotten it back. And I think almost anybody who's gotten it back has gotten a very, very high, like has gotten just about all the points. Maybe they like lost 1 point or 2. And if so, by the way, if you got a 24 out of 25, I think it was out of 25, or you got a 23 out of 25, do not bother to redo anything. It's not worth it. Like, you're awesome. It's awesome. That's awesome. And everybody else, no shame. Just do it. I mean, and you can use the benefit of all these class discussions to do it. But like, I'm really impressed how people that are doing things, you're all starting to actually use the 5-step like method of solving problems. And like a lot of you are like explicitly putting it right there. Like, here's my step 1. What's the question? Or excuse me, like, here's my diagram and fact pattern. And then some of you are using like computers and stuff to make the diagrams. It's gorgeous. Like the quality of the homework is like spectacular, really. And that is just a compliment to those people who've already turned it in. If you have not, you still totally can get all the points for being just as spectacular. And if you're taking your time to make sure you understand, great. But I'm very impressed. I think people are really learning how to do physics. I mean, even if those of you who think the problems are still too easy, I'm sorry about that. But I think you really are learning how to do physics properly. Anyway, my point is this. What I did notice on a lot of the homework 4s is that a lot of people thought that one of the issues of the different raw number sets was if you only had an even number of numbers, then that somehow, and I see that point, that's a very thoughtful point, that it looks like some of this wouldn't work if you had an even number of numbers, but it does, as long as we're clear on what we're saying is working. In other words, let's look at this for a second. Say I have the numbers 10, 20, 30, 40, okay? Like 4 numbers, an even set of numbers. And again, in my mind, that represents a car going 10 miles an hour, and then an hour later going 20 miles an hour, and then an hour later going 30 miles an hour, and then an hour later going 40 miles an hour. Now, here's my point. My point is the average of those numbers, the average velocity for that car, I can do in my head, it is 25 miles an hour. Now, note, it's very, very wise that many of you notice, like, wait, something funky is going on when you have an even number of numbers. Oh, yeah, something funky is going on. What's funky is that I just said that the average velocity for that car, a car that went smoothly, like from 0 to 10 to 20 to 30 to 40. And by the way, we're assuming this is all smooth. Like we're assuming unchanging change. So it's like if I measured every hour, I get these 10 intervals, but the assumption, especially if we're doing physics here, we're talking about motion through smooth space and through smooth time. If I think that in the next hour, the speed went up to 10 miles an hour, then I do think it follows from that if I had made measurements in half-hour intervals, the speed would go up by 5 miles an hour. In other words, A equals A naught means always changing by the same amount, not a cartoon, not a step function, not like it was going 0, it was going 0, it's going 10, it's going 10, it's going 10, it's going 10, it's going 20. Like, no, that would not be A equals A naught. A equals A naught means at any given point we check, the gain in velocity is the same. So if I have a list of numbers that's like 10, 20, 30, 40, even if I didn't happen to measure in the middle between 20 and 30, I say the average for that whole thing is 25, and check it, check it. When I say it's 25, I mean the middle number, like the middle between 10 and 40 is 25, right? And where did I come up with 20? And even though it's not a number that's in the original list, that is okay. It is still the number that's in the middle between 10 and 40, the middle of all that set. And specifically, how did I get the 25? Like, yes, you can check it. You can add 10 to 20 to 30 to 40, add them all up and divide by 4, and you get 100, like 40 plus 30 is 70, plus 20 is 90, plus 10 is 100, divided by 4. You could get it that way. But what I'm finally trying to say here is the faster way to get it. Once you believe that everything is stepping in a constant way, that everything is changing in an unchanging way, then not only is the median the same thing as the mean, but as it says at the bottom of the sheet here, or not only is the mean the same thing as the median, but that median can be acquired by just looking at the median of just the first and last. Like, please note, I'm saying 2 different things at the same time here. I'm actually really saying 3 things at the same time. I'm saying 1, the median average is the same as the mean average if and only if A equals A naught. So I'm saying 1, the median and the median, my God, no wonder I'm number 1, I'm saying the mean and the median are the same. Number 2, I'm saying that you can get that value, that median mean value, by just averaging the lowest and the highest. If I literally take 10 and add it to 40 and divide by 2, I get 10 plus 40 is 50, divide by 2, that's 25. That's the number in the middle. So even if that set were super long, even if the numbers were like 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, all the way up to 40, right? The average of the whole thing would just literally be the average of 10 and 40. I can ignore all of the middle data. That is a big revelation, actually. I mean, that's a big convenience gain that we're saying as long as you have this kind of pattern to the numbers, you can ignore everything that's happening in the numbers except for the very first and the very last. And the reason we're saying that is we're saying because the gains are always the same. So the top chunk is every bit in the top chunk is equally far away from the middle as every equivalent bit in the bottom chunk. So all of it can be, okay. So I'm saying three things here. The two things I'm saying are: one, median equals mean; two, median can be acquired by just taking the mean of the first and the last, right? And then the third thing I'm saying, and then I'll move on. Okay, this is such an important implication of it. To finally say something and finally maybe move on, we have like, okay, 18 minutes. This last bit I'm saying, and again, I know, hopefully I'm saying something to somebody somewhere. I know that some of you are sitting here thinking like, yes, I get it. And I do apologize. And I mean, I know some of you are sitting here thinking, I get it already. I got it last Wednesday. Please move on. Now, I am sympathetic to that. Again, I also want to say that for every person that's ever feeling, I get it already, can you please move on? I think, or for every 10 people that are feeling that way, I honestly think that like some percentage of them, like 3 of those 10, think that they get it, but actually new things are coming into their brain that they didn't even realize are new. And they did get it to a certain level last time, but they're actually seeing something new now that they didn't see last time. Or they feel that they got it last time, but in fact they were wrong about something, but they didn't know that. And now so partly why I do this, even when I think that you get it, is honestly, I think that there's levels and levels of getting. And sometimes we think we get things and it turns out we didn't get it. But also, I think repetition is really important. But also now I'm going to say something that I think I didn't say yet. I want to say that of the 3 implications that are tucked into this equation. Okay, so this equation, I'm talking a lot about this equation because it's our first double equal sign. This is our first equation that almost can feel like a formula or something because you can't always use it. But whenever you do use it, it's because you really need to. It's because something non-obvious is happening, quite frankly. Whenever we use this equation, it is as a technique and as a tool to actually get ourselves out of some problem that probably looks tricky enough to necessitate this. That's the honest truth. And you can see already that like it's tricky enough that there are times when it feels like this thing should be right, but it isn't. Like, let me say again, by the way, hill figure, when you go up the hill at 40 and then you come down at 60 and the average is not 50, you might actually stop and say, right, we might all stop and say right now, well, what was wrong with that? Like, where was the acceleration not constant? Which a good question, because honestly, it's worth thinking about for a minute. Because when we were going up the hill, acceleration was constant. And this is, and I'm tempted to ask a question, Matt. You could throw something in the chat now, right now, if you want, and you'll get like tons of points. I'm not going to pause because I almost think this will upset or embarrass people if I do. But watch if you're really with me right now, I'm going to sort of slowly ask a couple of questions. They're kind of rhetorical, like you totally don't have to answer them because they're trickier than they sound. But if you want to say anything in the chat or private chat, please feel free. Here's where, so I'm talking about hill figure for a second. If you go up a hill at 40 miles an hour, and then you take very little time to turn around and you come down the hill at 60 miles an hour. I keep referring to that because that is a classic. Like, and there's no other facts. I don't know how big the hill is. I don't care. Everything I'm saying about this hill would be true no matter how big the hill was. There's no other facts at all. Like, it was a homework problem. It doesn't matter. That's the whole homework problem right there. You go up the hill at 40 miles an hour, let's say, and you come down the same hill at 60 miles an hour and assume a very negligible amount of time, separates the both. So you got this trip and this trip, 40 and 60. Now, what I'm saying is the average speed for that is not 50. Like, that was an early thing we discovered in this class. That's a cautionary tale to say, don't think you could just always go around averaging speeds to get the average speed. There is an average speed for that, and it's 48 we found. And you can find that if you're really careful about understanding that average speed is distance per time. Put more specifically, the reason it's not 50 is because you spend a lot more time going 40 than you do going 60. How do I know that? Because 40 is slower than 60 and it's the same hill up and down, right? I mean, we talked about this, but if you go up, and it doesn't matter if it's up or down, it could be there and back. If you go a certain distance at 40 and then you come back that same distance at 60, necessarily it took you less time to come back that trip. And how much less time? Like 150% less time, like 3/2 less time, or 2/3 if you want to put it that way, right? Because 40 is 2/3 of 60. So if you wanted to average things out, the real proper way to average that would be like, it's not like averaging 40 and 60 evenly, fairly, equally. It's not, that's not fair. It's a weighted average because you're actually per time spending a lot more time on the 40 number than you are on the 60 number. So if you wanted to think of it as averages, you'd really have to think of it as like 40 plus 40 plus 40 plus 60 plus 60, add those up, divide by 5, and you get 48, right? We found that. Now, what I'm saying now is, well, how come that doesn't meet the condition? Like, how come that's not an A equals A naught situation? And that's a really good question, because when you're going up 40, here's the thing that you could put in the chat if you want or not. When you're going at 40, you do have a constant acceleration. When you're going at 40, assuming the 40 is constant, you do have a constant acceleration. Your constant acceleration, and if you want to put this in the chat, you can. When you're traveling at 40 miles an hour, nonstop 40, cruise control 40 miles an hour out, you have a constant accelerate. Or I think I am going to ask actually, and you can put it in private if you like. I'm going to ask now, when you're driving at a rate of 40 miles an hour for a while on cruise control, what is your acceleration rate? Like I have given you enough information to know it is a constant and it is knowable. If you're driving at 40 without changing your 40 at all, you're just going 40 miles an hour, 40 miles an hour, 40 miles an hour, 40 miles an hour for some region of space and time. What is your acceleration rate for that region of it's not a trick question, but it might be tricky since we're just learning about acceleration now. If you're going 40 miles an hour as your velocity is 40. what's your and always 40, always 40. I'm saying for this example, if it's always 40, what's your acceleration rate? If your velocity is perpetually, constantly 40, what's your acceleration rate? I guess I am asking. And anybody who puts anything in the chat, and it could be private. If you remember, if you put anything in the chat, you're getting points. If you put anything concrete at all, you're double dipping it at least into the for right or for wrong portal. And remember, if you're wrong, you're going to get 11 points for being wrong. So don't worry. Like, I'll even say this: if anybody actually private or publicly puts in the chat what my question is, that's definitely points to. I'm going to say the question again. My question of the moment. And I also know we are soon running out of time. I know that, but I've been babbling so much. I want to make sure we're still all together. So I'm picturing the Hill figure problem, but I'm just asking this excerpting question. Okay, I'm going to be, wow. Okay, I am going to repeat the question because someone asked, and I really appreciate that. I'm also going to note that someone in the direct chat did put in it. Oh, cool. All right, let me repeat the question. I'm getting some really good answers in the direct chat now. I am going to repeat the question because I appreciate that. The question is, but I want to commend the people in direct chat big time for their response. And I'm not saying that I'm not going to say their initials, but if you put anything in the direct chat, you are worthy of praise right now. Well, everybody's worthy of praise. Anyway, the question is, if something is perpetually going 40 miles an hour, like its velocity is perpetually, unchangingly, unwaveringly 40 miles per hour, what is its acceleration? That's the question. I'm going to wait just till and if even Lakshmi, which I really appreciate that if even Lakshmi even acknowledges that she now understands the question, she doesn't have to answer it. But if she says yeah, okay, got it, that would be closing the conversation. That would be really great. Okay, thank you. Great. All right, that's total points right there. Totally submit that. Okay, and now I'm going to wait for just any one other person. There's one person in the private chat who has said something totally profound, and because it's private, it's not giving anything else away to anybody else. So I sort of appreciate that too. It's a double advantage of private chat. Both, you don't embarrass yourself if that's what people are worried about, even though I wish you wouldn't be. But I understand. But also, the person who put something in private chat happy to actually say something right, but that doesn't spoil it for anybody else because I can't see it. Blah 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 blah. So I'm going to wait. But yay, and also yay to Lakshmi really for keeping this class moving along. So I'm going to wait for one more beat for anybody to put anything as an answer, possible, wrong or right, in public or private. The question one more time is, if you are going perpetually at 40 miles, if your velocity is perpetually, unchangingly 40 miles per hour, what is your acceleration? And it's not a trick question. It just might throw you off base if I haven't asked it yet before or something. I think you'll see the answer when you see it. I mean, I think you'll agree. I think you'll all agree to the answer once you see it. If you have an answer in your mind, it might well be right. I'll even give you one more hint. If the answer no, I'm not actually. I'm going to pause on this. And it really, even if in private chat, even if you, that's a great question in private chat. I'm going to read this out. Because I was actually just about to say something like this. Someone wrote in private chat, in direct chat, excuse me, is it a value? Or is it like in English? And then they said something else. But they're asking, am I actually looking for a value? Or am I just asking whether the value is or is not? Oh, I see what they're at. Okay. I am asking for a value. And I'm even going to tell you that I do think it's a constant value. It's a value. I can ask you this because whatever value you give me, I think it will be a constant. It would be true for the whole region. So that's a great question, and that's definitely points. And let me say also to anybody, even if you put in the private chat, I honestly understand the question, but I honestly don't have an answer. Or say, well, yeah, I mean, I think that would be something it says you're alive, which is helpful to me because I don't want to be a murderer, even though I suppose I look like one, and that's not funny. So why are you laughing? But yes, I'm looking for a value, and one person did already put it in private chat. And again, kudos to that person. But okay, fair enough. Someone in the private chat just said, I get it, but I don't know how to get it right now. Okay, I appreciate that. And I'll even take that as that I'm pulling teeth at this point, but I do want everybody to listen when you hear the answer, and don't feel tricked, please. When I tell you the answer, I don't want you to be like, oh, that's your point. Oh, gee, like, no, I mean, I want us all to acknowledge if we're literally listening right now, which I feel that we are, and we're really hearing the question. This is one of those this is where physics is psychological. Okay, don't be pissed off when you hear the answer, but recognize that this is why I take so long to explain these things in a way, or why we spend so long on fundamentals, because the fundamentals are sort of tricky. But once we get the fundamentals, then you can fly at any pace in physics, for real, for real, for real, whether it's with me or not with me. So let me tell you that if something is going perpetually, and again, let me praise the person in direct chat whose name I won't even say the initial, even though I kind of want to. But that person should definitely get points. Okay. If something is going perpetually at 60 miles an hour velocity, if something's 40 miles per hour, either one, if something's velocity is unchangingly 40 miles an hour, then it has a constant. So if it has a constant velocity of 40 miles an hour, then it definitively has a constant acceleration of value 0, which someone put in the chat. And that is not a trick, and it's not to be obnoxious, but it's meaningful information. Acceleration means change in velocity per time. If you know for a fact that your velocity is not changing, that doesn't mean your acceleration is your velocity. Notice, this is why this is worth talking about. I'm saying a car that's going 40 miles an hour, 40 miles an hour, 40 miles an hour has a constant acceleration. A car that's going 40 miles an hour, 40 miles an hour, 40 miles an hour of velocity has a constant velocity of 40, 40, 40, 40, 40. Well, if it has a constant velocity, it necessarily then has a constant acceleration. Its acceleration is not 40. I mean, they're not the same thing. They're not the same idea. But if its velocity is not changing, then its acceleration is constantly 0, because acceleration means change in velocity. If a car went 40, 41, 42, 43 miles per hour every hour, then its constant acceleration would be 1 mile, right? If you're every hour changing your velocity by 1 mile an hour, if every hour you're changing your velocity by 1 mile an hour, then you have a constant acceleration of 1. You wouldn't have a constant velocity then, right? Your velocities would be changing, but they'd be changing in a constant way. I mean, these are different. So acceleration is the speed of the speed. Speed or velocity is how fast your car is going. Acceleration is how fast your speedometer needle is going. If you see what I mean, right? Like you could be cruising at 40 miles an hour. You have a lot of velocity, always 4, but your speedometer needle is sitting there at the number 40. If you're going at 40 miles an hour velocity constantly, you have a constant acceleration of nothing, 0. But if you were speeding up progressively, 40, 41, 42, then you'd see your speedometer needle progressively, smoothly moving across like the. Yes. Oh my God. Okay, I feel like learning is happening. So Alyssa just put in the public chat, and thank you for doing that. And thank you for going public. And that's total point. And it counts as a for right or wrong thing, because she literally just made it. So what Alyssa put here in the chat is, so when it goes down the hill, next stage, at constant 60 miles per hour, then the constant acceleration would be 0 to, yes. So when it's going up, that puts it perfectly in perspective. And I'm looking at the time because I'm probably getting so excited. Class is probably just about over. Yes, right. Okay. So we have like 3 minutes. When the thing is going up at 40 miles per hour, it's going up at a velocity of 40. It has a constant acceleration of 0. Then it very quickly, but necessarily changes its velocity to 60, right? Like at the top of the hill. Say it does that in like 1 minute or something, like a short amount of time, but some amount of time, then all of a sudden it has an acceleration of like 20 miles per hour per minute, right? I mean, on average, right? So it hops from 40 to 60, but now it's coming down at 60 miles per hour velocity. So once again, its acceleration would be 0. I mean, she put it exactly in focus Alyssa, by saying that, like, whether your velocity is perpetually 40 or your velocity is perpetually 60, as long as it was perpetual for both, then the acceleration was 0 for both. So either of those two segments would count as a constant acceleration segment. And this new equation that, okay, we didn't get to practice so much today, but we hopefully talked about, this new equation would apply. I don't know how much help it would do, but it would be true for the up segment or for the down segment, because of what Alyssa just said, and because of what private chat person, may he be praised or she be praised, said 5 minutes ago. Like, yes, either one of those segments has an acceleration of 0, but the original problem asks, what's your average velocity for the whole thing, for the whole round trip? And even though this may sound like a technicality to some of you, it's a reality. It's not a technicality, it is a reality. That for the whole round trip, if we looked at accelerations went like this for the whole round trip. They went 0, and then 20 or some like huge number, and then 0 again, right? 0 for the up trip, 0 for the down trip, but some big number for the middle part that is definitely there for the, if we changed from 40 miles an hour to 60 miles an hour, even though that might, and you might say, well, I thought that took a really small amount of time. Yeah. Let's assume it took a really small amount of time. So if it took a small amount of time as a minute, then the acceleration there was 20 miles per hour per minute. If it was a smaller amount of time, like a half a minute, then it was twice that accelerate. Then the denominator got smaller by a factor of 2. So the whole fraction doubled. In other words, if we raised from 40 miles an hour to 60 miles an hour, if we raised up by 20 miles an hour in a half a minute, then that's an acceleration rate of 40 miles per hour per minute. Or if we did it in a second, then it's like 20 divided by 60. It's like, then it's like, I just forgot what I was writing. Oh, then it's like multiplying by 60. So it's like 1,200 miles per hour per minute, right? In other words, the shorter amount of time, the less we had to count it for displacements or times or velocities. But the bigger that would make the acceleration jump. If so, for this whole round trip, we didn't have one acceleration for the whole round trip. No way, definitely not. We had 0 for a big portion, 0 for another portion, but some crazy high number for the middle portion. So the average velocity for the whole round trip was not the average of the beginning and the last velocity. This last equation works only when it works. It only works when you have a reliable pattern in the velocities. When acceleration, when velocity is changing, but in an unchanging way. It works only when acceleration is a true constant throughout the whole thing, whatever whole thing you're talking about. But that was real. Those of you who participated, again, whether it was private or public, I really appreciate it. I hope the rest of you understood what I was talking about. And I hope this wasn't too much about too little or too little about too much. But I think that's our third equation. I think we understand it now. We will just keep doing the homework wherever you are. Nobody is late, nobody's behind, but there is at least one more homework that we have to, so there's no new homework or anything. Just do whatever you're doing wherever you are. But people are doing very well with it, and I appreciate it. Okay, so I'll hang out for if there's any more questions, but we're done. Thank you so much. Thank you. Have a good, thank you. Have a good next 2 days. I'm just gonna change the view.
Versa, I had a quick question.
Yes, and we just